Welcome to the exercises for chapter 11. This chapter is all about t-tests. T-tests are super important. They are used so often. And fortunately, t-tests are also really simple to implement. And so the goal of exercise 1 is to produce a t-value and a corresponding p-value on your own without using SciPy. And then, then you want to compare your results to the output of SciPy's t-test function to make sure that you are getting the correct answer. Okay, so to start with, you're going to generate a data set of 50 numbers randomly drawn from an asymmetric Laplace distribution. There's a function in scipy.stats called Laplace asymmetric. You can use this function to generate random numbers that are drawn from an asymmetric Laplace distribution. And you need one parameter, it's called kappa. You can use the value of 2 to reproduce the results that I am showing here. Well, there's some randomness in here, but qualitatively reproduce my results. Now, there is nothing particularly special or meaningful about an asymmetric Laplace distribution as it regards to the t-test, but I think it's an interesting distribution, and I like to give you some additional things to just expand your knowledge of numbers and statistics, distributions, and so on. So anyway, once you generate this distribution, you can plot the distribution. Looks something like this. You see all the data points here and a histogram over here. Here is the empirical mean, the average of this particular sample in the black dotted line. You can see that in both of these plots. And then you want to test the null hypothesis that the mean is minus pi over 2. And that you see in the dashed line. Again, minus pi over 2 is nothing special. It's just like some cool looking number that I came up with. The point here is to make sure that you understand the t-test formula well enough to implement it in Python without using SciPy or SciPy's t-test function. Okay, so yeah, generate a plot that looks like this. And then what you want to do is compute the t statistic and then compute its corresponding p-value using stats.t.cdf. And then print that out. So that is this line here, manual t-test. And then you want to perform the t-test using scipy.stats.ttest _1samp for one sample. And then print out both of your results here and make sure that they match. If these numbers don't match, then it means that something went wrong somewhere and you have to fix it. So here I'm setting up the parameters, sample size, null hypothesis value. Here's where I generate the random data, and here is the mean of those data. I've discussed this general format before, but RVS is for random variates, random numbers drawn from this distribution. Okay, and then the rest of this code is just some plotting, not super interesting. That reproduces the figure that I showed in the book text. Okay, now for the t-test. You can see the calculation of a t-statistic is super simple. It's the sample mean minus the null hypothesis value. Now, in many cases, the null hypothesis value is 0. So oftentimes in practice, you can just omit this. The numerator of the t-test is just the sample mean. But here we do not have a null hypothesis value equal to 0. We have a null hypothesis value equal to minus pi over 2 for some crazy reason. Okay, and then the denominator is the standard error of the mean, which is the standard deviation divided by square root of the number of samples. So then we have the t statistic, the t value, which is just the ratio of these two. Obviously, you could put all of this into one line of code, but I've discussed this before that, I think when you're translating math into code, it's not necessarily advantageous to put everything in one line, to have one formula correspond to one line of code. Very often it's useful to have one formula, one expression correspond to multiple lines of code. Just makes it easier to read, less likely for you to make little coding errors and so on. Okay, so here we got the p-value. This is the cumulative distribution function of the t distribution. And then we want the absolute value of the t-test with this degrees of freedom, n-1. We want the absolute value to make sure that we are getting the probability value, the cumulative probability value that's all the way to the right of the distribution. Then we take 1 minus that, which is going to give us a small value. And then we have to double it because we are doing a two-tailed test. I never specified that we want to test whether the sample mean is greater or less than minus pi over 2. So if you don't specify the direction of the test, you always assume that it's two-tailed. And here is the same results using scipy.stats.ttest one samp. So you input the data sample and then the null hypothesis value, and you get out this object here from which you can extract the statistic, which is the t-value, degrees of freedom, and p-value. And now I'm just printing out. Now, if you don't see that these two sets of numbers are identical, then something went wrong somewhere. The most common source of mistake here is to forget that you have to change the p-value when you're doing a two-tailed test. So this right here is a very easy mistake to make. If you find that the t-values match, but the p-values don't match, then that is almost certainly the issue here. Here we are in exercise 2 of chapter 11. This exercise follows directly from the previous exercise, including using a lot of code that you wrote for the previous exercise. So definitely make sure you went through exercise 1 before this exercise. Okay, so we found that the p-value was greater than 0.05, indicating that this test was not statistically significant, which indicates that we cannot say that the sample mean is different from the null hypothesis value of minus pi over 2. And basically what that means is I don't know for sure what was the mean of the true population that we drew these data from, but I cannot say that it was not equal to minus pi over 2. It could have been equal to minus pi over 2. To be clear, this test does not mean that the population mean was equal to minus pi over 2. That's not what it says. What the test says is that I don't know for sure that the true population mean was not equal to minus pi over 2. Okay, so the question that we are addressing in exercise 2 is how stable that result is. As you know, we are generating random numbers, so these values, the t-value and the p-value, will change every single time you rerun the code. The test, the formula is exactly the same. The distribution is the same, but the random numbers are going to be different. Okay, so to find that out, you are going to take the code from the previous exercise and embed it into a for loop that goes over 500 iterations. So that means 500 times you are going to draw random data from an asymmetric Laplace distribution. Each sample is 50 data points. So draw a random sample of 50, compute the mean, test the mean against the null hypothesis, and record the t-value, the p-value. Now, in this case, you are also going to want to store all of the sample means and sample standard deviations. So inside this for loop, over 500 iterations, you generate some new random data, get the mean, get the standard deviation, do the t-test, and determine whether it's statistically significant. After that for loop, then you want to go and make a plot that looks like this. And what you see here is all of the means and the standard deviations for all 500 of these iterations in our experiment, corresponding to or separated by whether they had a p-value less than 0.05 or p-value greater than 0.05. So obviously your figure will look slightly different from mine because of randomness, but it should look qualitatively similar. Okay, I have a couple of interpretational remarks about these plots, and I'm going to discuss that after I create this figure in the code. After having gone through the previous exercise, and if you are more than a basic Python coder, I don't think that you will have a lot of problems with this, the coding part of this exercise. So here I just initialize some variables that I need for, whether it's significant, and getting the means and standard deviations. You can see here, I don't actually store the p-value. I'm just storing a Boolean, true or false, whether each test was less than or equal to 0.05. And that's because, it's because for the way I specified this experiment, instructions, you don't actually need the exact p-value. Okay, so here's a for loop over all of our experiments. Now, it turns out that you do not actually need a for loop to run this experiment. That is not part of this exercise, but if you like, you can do this for an extra challenge. Or if you're not sure how to get rid of this for loop here and just vectorize everything, don't worry about it for now. Just wait until after the next exercise, and then you can come back to this one if you like. Anyway, you will recognize a lot of this code from the previous exercise. So here I generate random data. Here, well, I'm just using the scipy.stats module. You don't need to write out your own code anymore for the t-test. Okay, and then you can see here I'm storing whether this test was statistically significant, whether it had a p-value less than 0.05, and I'm also storing the mean and the standard deviation of each of these samples. Okay, then I print out the results and generate the figure. So the results are that with a p-value threshold of 0.05, I found a statistically significant mean difference from minus pi over 2, the null hypothesis value, in a little less than 10% of times, so 40 out of 500 times. Okay, and here you see the plots of the sample mean and the sample standard deviation. And what you see is that, if you think about a distribution, like imagine the marginal distribution of all of these means, the distribution centers, so where the means are closer to the middle of the distribution, those tended not to be have a p-value less than 0.05. And where you do see the p-value less than 0.05 is where the means are towards the tails of the distribution, so relatively high or relatively low, and also that the standard deviations tend to be relatively small. Now, all of this is purely by chance, right? There's not, it's not like I changed the random parameters for these tests versus these tests purely by chance. Sometimes you just draw 50 random numbers from the universe, and you will just happen to find sometimes purely by chance that sample happens to have a relatively small standard deviation and a relatively extreme mean. And those are the cases where the t-value is going to be large and the p-value will be small, less than 0.05. You have now performed a t-test in code many times earlier in this chapter and also in the previous chapter. And so far, all the times that you've run a t-test have been in for loops. So if you have 10 tests that you want to do, then you have to have a for loop that goes over 10 iterations. And at each iteration, you perform a separate t-test on each of 10 data sets. That's fine. For loops are great. Human civilization would come to a screeching halt without for loops, but that doesn't mean that for loops are always necessary. And sometimes it's good to avoid using for loops. It makes your code shorter and cleaner and more efficient, more compact, and so on. So the goal of this exercise is to make sure that you know how to use the scipy.stats.ttest function to test multiple samples at the same time. So basically a way of getting rid of a for loop, like what we were using in the previous exercise. Now, the way that you do that is by using a matrix input. So far, we've been inputting a vector into the t-test function. So we've inputted one vector corresponding to one sample. So the idea is, imagine you have 10 samples that you want to get t-values from. Then basically you take each of those sample data sets and you put them all into a matrix as columns. So the rows are observations and the columns are the different tests that you want to perform, or the different samples. Now, one word of warning, this is valid. This approach is valid only if all of your samples have exactly the same sample size. If your samples have different sample sizes, then you would actually need a for loop, or at least multiple calls to the t-test function. Okay, but anyway, so what you want to do here is create a data matrix of 40 by 20. So the matrix size is 40 by 25, corresponding to 25 data sets, and each having a sample size of 40. So you can use normally distributed numbers drawn from a population with a mean of 1 and a standard deviation of 1, and then test against the null hypothesis of 0. You can, you can use different data character. It doesn't actually matter. The important thing is to have this matrix size with 40 observations and 25 samples. And then the idea is you're going to input that one matrix into the t-test one sample function, and then separately write a for loop. So this is, for loop like now what we're going to start calling the old school method of doing these t-tests. And the reason why you want to do that is you want to make sure that you get identical output. So you shouldn't get different outputs, different t-values when you use a matrix input versus without a for loop versus vector inputs inside a for loop. Okay, so yeah, then just print out your result. And I'll have a few more things to say about this approach when I switch to coding. So here is where I generate the data. You can see that it is random numbers drawn from a normal distribution that has a population mean of 1, a population standard deviation of 1, and this is going to be the size. Okay, and then here I'm printing out the shape, the size of this matrix, just to confirm that it is the correct orientation. All right, so now, this is super simple, right? You just call this function once with this matrix in here versus setting up this for loop here. So we can do these 3 lines of code that we can do here like this. So then what we should find is that these results and these results match, and that's what I do here. So printing out all of those results, and yeah, you see that they're all the same. Now the exact numbers are random, right? I mean, these are just coming from random numbers. Don't pay any attention to the fact that these are 7s and these are 6s. That's not important. What is important is that this number is the same as this number. So each row should have 2 identical numbers. That's what is important. Now you can contrast that. Let's say we transpose the matrix like this. So now we are inputting the matrix the other way around. And now you see when we do the for loop versus the matrix input, we get different results here. These t-tests are not the same. And why are they not the same? Because we've changed the orientation of this matrix. So now what we are actually inputting into SciPy is a matrix that is 40 samples, each sample having 25 observations. So it's the wrong way around. So it's a really powerful technique because you can avoid using for loops, but it's super duper duper mega ultra important to make sure that you are really confident that you are inputting the matrix in the correct orientation. Otherwise, your results will be completely wrong, and you obviously do not want that. When you're implementing this in practice, especially the first time you're writing code for an analysis, it's a good idea. I recommend doing this to run through this, do this for loop at least once, just to confirm that this is really the correct orientation. Welcome to exercise 4 of chapter 11. This and the next several exercises will focus on decomposing the t-value, the t-statistic, to gain a better and deeper understanding of what contributes to a significant t-test. As you know, the t-statistic is based on a ratio. It's the ratio of the mean of a sample or the difference of the means of 2 samples divided by the standard error of the mean, which is the standard deviation divided by the square root of the sample size. Okay, so in this exercise, we are going to focus exclusively on the standard deviation. So we're going to manipulate the standard deviation and explore how that impacts the t-statistic. So here's what you want to do. Create a data set of 40 numbers randomly drawn from a normal distribution where the standard deviation of that distribution ranges between 0.1 and 3 over 300 different iterations inside a for loop. So that means that the first iteration in this for loop, that's going to be the first data set that has a random numbers drawn from a population mean of 0 and a population standard deviation of 0.1. And then each subsequent data set is going to have a larger and larger standard deviation going up to the final iteration in the for loop, which is the 300th data set, and that will have it'd be 40 numbers randomly drawn from a normal distribution with a population standard deviation of 3. Okay, so then what you want to do is force each sample mean to be 0.5. Now, this is not the input that you provide to NumPy's random distribution number generator function, because the population mean should always be mu equals 0, but you want to force the sample mean, the empirical sample mean, to be 0.5. Okay, and then you perform a one sample t-test, and at each iteration store the t-value, the t-statistic, and the p-value. Then you can make plots that look like this. So here you see the standard deviation. This is the population standard deviation on the x-axis, and the t-value over here. And here's for the p-value, so same x-axis. And here you see the t-value plotted by the p-value over here. I will have several remarks about these plots, which I will discuss in the coding section. So here I set up some parameters. There's a sample size of 40 over 300 different iterations. This is the range of standard deviations that I'll use. It's just initializing some stuff. Don't worry about this line of code here. This is actually for the next exercise. So I'll talk about this in the next video. Okay, so here we have our for loop. This is our experiment. We generate random data, 40 random numbers drawn from a theoretical normal distribution with a population mean of 0. And this has a population standard deviation of 1. So then I multiply all of these numbers by the corresponding standard deviation. Then I do a t-test, and I get the t-value and p-value. Very straightforward. Again, this line is for exercise 5. You don't need to worry about it for now. All right, and then we do some plots. So really straightforward. Actually, the code is pretty simple. So it's interesting to see that, oh wait, now it's going. Sorry about that. The server disconnected. I had to re-import NumPy and so on. Okay, so here we see the plots. So it's interesting to see that the t-statistic changes so drastically, right? It goes from like 35, maybe it's close to 40, all the way down to some t-value close to 0, while the numerator of the t-value is exactly the same. I know that the numerator of the t-value is exactly the same because I am forcing the mean to be 0.5, the mean of every single sample in this, regardless of the standard deviation. The mean is guaranteed to be 0.5, and that is the numerator of the t-test. It's 0.5. So the numerator has not changed at all, and yet only the standard deviation has changed, and yet the t-values change by, like, I don't know, what is this, 2 orders of magnitude or something, 1 or 2 orders of magnitude. Drastic changes. And you see that also in the p-value. The significance threshold for any individual test would be 0.05. So that's around here. So you see these tests go from being highly, highly statistically significant with a small standard deviation going up to very non-significant. And now, on the one hand, when you think about the formula for the t-value, that is not at all surprising. Of course, as the standard deviation gets bigger, that's in the denominator. So the whole fraction gets smaller when the denominator gets bigger, even though the numerator isn't changing. So mathematically, that is not surprising. But in terms of the practicalities of doing statistics, designing experiments, thinking about the results you might get, this actually is very important to understand, because you can have the same effect in your data, so the same magnitude of difference, the same size of the effect, but if the variance is high, if the standard deviation is high, then you're not going to get a significant effect. Exercise 5 of chapter 11 is just a minor follow-up to the previous exercise, so you definitely need to have gone through exercise 4 before getting to this exercise. So it's very simple. Actually, let me go back up to this figure here. So here, what I'm plotting on the x-axis is the population standard deviation. This is the expected standard deviation, but the sample standard deviation is not going to be exactly equal to these values here, just because of chance, sampling variability, finite samples, and so on. We only have 40 samples, so the sample standard deviation is not going to be exactly equal to the population standard deviation. So the question we are answering in exercise 5 is whether that matters. So would it change this relationship if we change this x-axis from instead of plotting the population standard deviation, the theoretical standard deviation, instead we plotted the empirical standard deviation. So pretty straightforward. And if you watch the video for the previous exercise, you see I already had the code in there for this exercise. So anyway, now I'm going to switch to Python and discuss a little bit about this question. This right here is the code for exercise 4. And yeah, I've already mentioned that here. So I didn't talk about this in the previous video, but I just said it's for the next exercise. So you see, all I'm doing is computing the empirical standard deviation. This is the sample standard deviation, and I store that in variable s. So if you like, you can reproduce these actually, I guess I'll just do it now. So now instead of using this variable, standard deviations, this is the population standard deviation. Instead, I'm using the empirical standard deviation like this. And basically, it doesn't change the results that much. I mean, technically, numerically, the plots are slightly different. They're a little bit cleaner. And why are they a little bit cleaner? They have less noise. That's because well, let me show you here why that's the case. Here I'm looking at the correlation between the population theoretical standard deviation and the empirical standard deviation. And then I'm just plotting them. So you can see that they match really closely. The sample standard deviation is a really good estimate for the population standard deviation, especially for small standard deviation values. So this is why the conclusions that we drew in the previous exercise are not really different when we visualize the population standard deviation or the sample standard deviation. You can see that the relationship is still pretty strong, but it breaks down a little bit for higher standard deviations. And that is why this looks cleaner up here compared to, let me go back to change this back like that. Yeah. So make a mental image of this plot. So it's a little bit messier here with the population standard deviation. And that's because, and then up here as well, the population or the sample standard deviation is less closely coupled to the population standard deviation for larger and larger standard deviations, especially when the sample size is fairly small. If you like, if you're curious to follow up on this concept, you could try to increase the sample size. So from 40 to, set it to 100 or 500, and you will see that this relationship starts to get really, really tight. Here in exercise 6, we are continuing our in-depth investigation into the different components of the t-statistic and how that affects statistical significance. In particular, we are here going to focus on the numerator, which is the difference in the means between the one sample and another sample, or between one sample and the null hypothesis value. And we will simultaneously and orthogonally investigate the impact of sample size. Okay, so what you want to do is design an experiment where you manipulate two factors independently of each other. We have the sample size and the theoretical population mean. So the sample size will vary between 10 and 810 in steps of 50. So that means you'll have samples with sample sizes of 10 and 60 and 110 and so on, up to 810. Okay, and then you are also going to vary the theoretical population mean that you use to generate these random numbers, starting at 0 and going up to 0.3. So not a huge effect, but still, it's an effect in 51 steps. Okay, so let's see. So then that's going to give you a double for loop where you are going to manipulate each combination or test each combination of sample size and theoretical population mean from which you are drawing random numbers. Okay, and then inside that double for loop, you want to create 250 independent data sets. Okay, and use sigma or population standard deviation of 1.5 for all of those simulations. I hope that makes sense. So you're going to independently manipulate the sample size and the theoretical population mean. And within that double for loop, you are going to create 250 data sets. And always, we just keep the sigma value constant. Okay, so then you want to compute a t-test on all of those 250 data sets against the null hypothesis of 0. We don't care about the t-values. We don't care about the p-values. All we care about for this exercise is the proportion of data sets that had a statistically significant effect size, so p less than 0.05. Okay, so then you store all those results, and it's going to produce a matrix that looks like this. So here we see the mean. This is the theoretical population mean. Here is the sample size on the y-axis. And the color here corresponds to the percent of tests with a p-value less than 0.05. Now, this is what your result should look like if you successfully implement this exercise. I'm going to interpret this plot and say what it means about the t-statistic and about statistics in general when I show you this plot in Python. So here I'm just initializing these variables, the mean, population means, and the standard deviations. And let's see, here's our double for loop. So we're looping over different sample sizes and different, I call this variable effect, but it's basically just the theoretical population mean. So now you can see that I'm generating a matrix of numbers, just like what I showed in, I forget which, a couple of exercises ago. I showed you how to run a bunch of t-tests simultaneously on a matrix of numbers. And that's what you see here. So the sample size by the number of experiments, which is 250. Okay, so then we can do a t-test on all of those values at the same time. And then here I'm getting the proportion of the p-values that are less than 0.05, multiply it by 100 to get percentage. You can do whichever one you want. It doesn't really matter. It's a little bit arbitrary. Okay, and then I'm showing that matrix here. Okay, so here is the matrix, and, oh, it's still running. Okay, here we see this matrix. So what does this mean? First of all, let's just think about this in terms of the experiment. So this cell over here, this one right here, corresponds to a simulation, one out of the many, many simulations that we ran in this experiment, where the mean offset was around 0.7 and the sample size was 310. And so this color, I keep forgetting which one I'm pointing to, but this color value here tells us that, whatever, let's say 15% of these tests out of 250 total tests, 15% of them had a p-value less than 0.05. Okay, so that is just how you interpret this. Basically, white colors mean more of the tests would be considered statistically significant, and black would mean that very few tests would be considered significant. And so basically what you see is that there's this nice gradient over here in this two-dimensional space, such that you are more likely to get a p-value less than 0.05 with a large sample size and or with a large effect, so a large mean offset. So this is important to understand because it means that if you want to get a statistically significant result, you need either a large sample size, well, not just a large sample size, but you need a large sample size, and you also need the effect to be pretty big. This graph also indicates that if you don't have a large effect, so the mean difference is fairly small, you're looking for a subtle effect in your experiment, you need a really big sample size in order to get that effect to be significant. You can see here, for example, with a mean difference of 0.1, so this is less than 1/10 of a standard deviation. Even if you have a sample of 200, most of the time you're not going to get a significant result. So you really need a big sample size if you have a small effect. Welcome to exercise 7 of chapter 11. In this exercise, we will combine the idea of data transformations, which was a focus of an earlier chapter, with the paired samples t-test, using the example that I presented earlier in this chapter called the reading comprehension study. This was fake data I made where the idea of the study was to measure reading comprehension in a quiet environment and a noisy environment and perform a paired samples t-test to determine whether the comprehension levels were different between those two noise levels. Okay, so you don't have to worry about the details. The data are also in the online code, so you don't need to, I'm not going to go back to page 22. Okay, so the idea is you're going to perform 4 paired samples t-tests on the same data, but after applying different transformations. Now, as you know, the paired samples t-test is implemented as a one sample t-test where you first subtract the pairs, and then you just do a one sample t-test on the difference. Okay, so here are the 4 variables that you will perform a paired samples t-test on. This is actually no transformation here. I just call this simple subtraction. So data from the quiet condition minus the data from the noisy condition. So that's, I'll call that variable y1. And then we have z-score subtraction. So here, it's exactly the same thing, except first you normalize, you standardize the variables, and then you subtract them. And then we have percent change, and I see there's a little typo here. This should be xn, so it should be this thing. I'll fix that in the text before you reading this book. And then we have this normalized ratio down here. So this is quiet minus noisy divided by quiet plus noisy. This is a common ratio that's used. Okay, so let's see. So first, what you want to do is perform draw a bunch of scatter plots showing how all of these variables relate to each other. So scatter plot of y1 and y2, y1 and y3, y1 and y4, and so on for all these possible pairs. Now, the thing is that all of these transformations come from exactly the same data. We're not changing, we're changing the data in the sense of normalizing, but we're not using different data. It's all the same data. So it's interesting to see that some of these variables are really closely related to each other, like the simple subtraction, which is no transformation, and z-scoring, and others are actually not. So, I mean, it's still strongly correlated, but, you know, there's some points here that are different from each other after, for example, percent change and z-score. Okay, so then you want to perform a paired samples t-test on these 4 variables and look at the results. And I will show you all of those t-test results in Python. So here are the data. This is comprehension in the noisy condition, comprehension in the quiet condition. Of course, they have to be the same sample size because they are paired. They go together. Each one of these comes from the same individual, the same participant in our research study. Okay, so then here I have all the different transformations, pretty straightforward. So this is just no transformation. Z-scoring, you can see I'm Z-scoring each individual variable. I'm not Z-scoring the difference, percent change, and this normalized ratio. Okay, so then the rest of the code in this cell is just generating this scatter plot here. So there we go. Again, yeah, you see some of these variables look really, really similar. The correlation would basically be 1. Some are very, very close to 1. And in other cases, I didn't actually compute the correlation coefficient, but maybe you want to add that. You can compute the correlation between each pair of variables and report that in the title of each subplot. That would be interesting. I guess this is also above 0.93, something like that. Okay, so then we get to the t-tests. Pretty straightforward, as I've mentioned before. Once you know how to implement a t-test and calculate the t-statistic and so on, you don't want to do that stuff by hand. You just use the scipy.stats function. In this case, we want t-test one sample because we are doing one sample t-test on the difference, and the null hypothesis value is always 0, right? So if the 2 conditions are equal, then one condition minus the other condition should equal 0. Okay, and then here I'm just reporting out the t values and the p values. So let's see what we get. Oof, look how different these are. This is shocking. This is really crazy. We have exactly the same data and we applied very simple transformations, and yet we get completely different results. We get different t values and different p values. Now, I can start by interpreting this one. So this is the z-score. By definition, when you standardize a variable, it's going to have a mean of 0. So when we compute this, which has we force the mean to be 0, and here we force the mean to be 0. of course, the difference between these two is going to be 0. So therefore, it's trivial that the sample has to equal the null hypothesis. It cannot be any other way. That's why the t-value is exactly 0. The numerator is 0, and the p-value is 1. Okay, and then, maybe percent change and normalized ratio, you're not too concerned about the difference because those are really similar to each other, and they're both on the same side of 0.05, right? So in both of these cases, both of these transformations, you would still come to the same conclusion that there is an effect of our manipulation. Maybe the sample size would differ a tiny bit, but anyway, but this is weird, right? So we perform the t-test without doing any transformation, and now we get the opposite conclusion. If you saw these data, you would conclude that there is no statistically significant effect of the noise level on reading comprehension. Maybe you could call this a marginal effect because it's less than 0.1. But still, this with no transformation and with transformation is a different statistical conclusion about exactly the same data. Now, that is annoying and frustrating and confusing. There is one reality, and is it like this or is it like this? What is the correct way to normalize data? That is unfortunately very difficult to say. It has to be evaluated on a case-by-case basis. It depends on the nature of your data. That is, say, whether and which transformation you should apply. So this is very difficult situations in practical statistics. Fortunately, I will say that the larger the sample size, the lower the risk of something like this happening. So I would guess, I haven't tried this, maybe you can try this if you're curious, but I would guess if you would have, let's say, a sample size of 20 instead of 10, then this discrepancy would go away. I don't know if that would be true. Obviously, it would depend on the numbers that you write. But anyway, I wanted to include this because I think it is important for you to understand as a practicing data scientist that these things can happen, and it's never really clear what is the right thing to do. In this case, what is the right decision to make about how to normalize the data. Welcome to exercise 8 of chapter 11. The purpose of this exercise is to continue our exploration of the different features of a t-test and what makes a t-test be statistically significant or not statistically significant. So we have previously explored the one samples t-test, the paired samples t-test. Now we are going to explore the independent samples t-test. So two samples t-test. And basically, in an experiment that you set up, you're going to vary the sample sizes of the two samples that you draw from these two different populations. So we have two populations, one both normally distributed, one with a theoretical population mean of 1, and the other with a theoretical population mean of 1.2. So this means because we are simulating, we have ground truth data, we know the true population means are different by 0.2. The question is whether our randomly drawn samples will show a statistically significant difference of the sample means, given that we know that the population means really do differ. Okay, and then use a standard deviation of 1/2 for both of these. This says samples, but this actually should say population. So the population standard deviation should be 1/2. Okay, so here's what you do. To start off, you generate 10 samples from population 1, 10 samples from population 2, and then you perform a 2 samples independent t-test, and you want to record the t-statistic and the p-value from that run. Now, then you want to increase the sample size to 20 for both samples. So in the first iteration, it's 10 samples, and then you have 20 samples from population 1 and 20 samples from population 2. Run a t-test, store the t-value and the p-value, and so on, all the way up to 200 samples, 200 data points from each sample. Okay, so then because we are sampling random numbers, we want to get a better sense of the distribution of t-values, run each of these experiments 100 times. So create 100 pairs of samples for each sample size. Okay, I hope that's clear. And then basically you're going to get or produce a plot that looks something like this. So there's two panels. I'll discuss this one first. Here we see the t-values and the sample size on the x-axis. So what this means is that for this iteration of the experiment loop, there were 100 pairs of samples from each of these two populations, and each sample had a sample size of 70. And then you see all the t values from the t-test, and basically the gray boxes are the non-significant, so p greater than 0.05, and the red circles are p less than 0.05. Okay, so I hope that's clear. So we do 100 iterations at sample size of 10, 100 iterations at sample size 20, and so on. Here in panel B is exactly the same plot, except it's the p-values instead of the t-values. So basically plotting the same thing. And then you can make some observations and remarks. I'm going to talk about these plots in more detail when I generate them in code in a moment. But there's one final component to this exercise, and that is, you can see where the t-values are becoming statistically significant here, right? Now, this is the significance based on looking at the p-value. But as I discussed in this chapter, you can also compute what's called a critical t-value. The critical t-value is the t-value, the exact numerical value of the t-test that you would need in order to get a p-value less than 0.05. And of course, that is going to change slightly for each degrees of freedom, so corresponding to the sample sizes. So the last thing to do in this exercise is to make a plot of the critical t-value as a function of the sample size. I don't have that plot here in the text, but I hope you get what to do. It's not so difficult. And yeah, then of course I'll show the code to generate that plot in a moment in Python. So here we are in the code. You can see I'm defining these two population means here. And well, I wanted to soft code these so that once you have this code up and running and you understand how it works and what it shows, then you can change these parameters and continue exploring the impact of sample sizes on the statistical significance. So, for example, what happens when you make the mean differences smaller? How often do you see erroneously statistically significant results when the population means are the same? Lots of interesting things you can do, but for now, I'm going to keep this at the instructions that I specified. Okay, here we see our range of sample sizes. And let's see, here is the experiment. So we loop over the different sample sizes. Here you can see I'm generating random numbers from a normal distribution with a population mean of 1, population mean of 1.2. They both have the same standard deviation. This is hard-coded, but it would be great if you want. You can also explore the impact of population differences in standard deviation. So maybe, if you set this to be, population 2 has half of the standard deviation, so much less variation in population 2. That's another thing you can explore. Okay, here I'm generating the size of this matrix, and you can see it's n by 100. So n is the sample size at each of these iterations in this for loop, and 100 is for the repetitions. So we repeat this experiment 100 times, generating new random numbers. So this actually produces a matrix of samples by repetitions. Now, I have shown you in a previous exercise that you can use matrix input into the one sample t-test. I didn't actually show you that matrix input also works for the independent two samples t-test, but well, it does. And maybe you figured that out already, which is great. Okay, so here we get, so here I run the t-test, extract the t and p values, and then I'm plotting them. And now I need pairs of plotting lines because I'm using separate markers and colors for the p-values that or the t-values that are statistically significant and not statistically significant. So then plotting the t-values and the p-values. So let's see, here we see the plot. And so some interesting things that you can see. First of all, you see that the whole distribution of t-values is shifting up as we increase the sample size, right? So very few significant tests here, and lots of significant tests here. Now, the thing is that these two populations still have the same mean difference of zero point 0.2 all the way across all these sample sizes. The population means have not changed. So what has changed is the sample size. So as the sample size increases, basically the standard error decreases, which means that the t fraction, the ratio, increases. So that's not so surprising. It certainly comes directly from the formula for the t-test, but I think it's really great to have empirical demonstrations like this. I think that really helps build intuition. Okay, the other thing I would like to point out is that it kind of looks like the significance, the dividing line between significant and non-significant samples is pretty flat across here. Now, that might be surprising because we have an order of magnitude difference in sample sizes. We go from 10 up to 200. So that's a 20-fold increase in sample sizes. And yet it seems like the dividing line between the significant and non-significant tests is about the same, right? So this is basically looks like a flat line all the way across here. And that is the idea of plotting the critical t-value. And so that's what I do here. So I use this inverse survival function basically as a more accurate measure of the inverse of the PDF. And I specify two inputs. First is the probability value. And here I'm using 0.05 divided by 2. So this would be a two-tailed test. And then this is the degrees of freedom over here. Okay, so then I'm just plotting the sample size by the critical t-value. And it's pretty interesting to see that it's pretty flat. I mean, you could zoom in a little bit more if you want. You could change this. Maybe I'll do this now. So let's set this to be maybe 1.8 to like 2.2. Try that. So you can see that the critical t-value does decrease as a function of increasing degrees of freedom, which correspond to increasing the sample size. But except for very small sample sizes, the increase is pretty gentle, right? I mean, this is only going down very, very, very gradually. So this is actually pretty interesting and not really so intuitive in my mind. So basically the story is that the critical t-value that you need to get a significant result is basically staying the same for a huge variety of sample sizes. But the larger the sample size, the cleaner the estimate, the better we can estimate the population means and the population standard deviations and therefore also standard errors. Needless to say, the conclusion of here is, it's good to have large sample sizes whenever possible. Here we are in exercise 9 of chapter 11. Now we are going to follow up on the previous exercise, looking at the independent samples t-test. So in the previous exercise, we manipulated the sample size of the two samples, but we fixed the population standard deviation. And so now what we are going to do here is keep the sample sizes fixed. They're actually different for the two samples, but they are the same for all the iterations in this experiment. And instead, what we are going to manipulate is the standard deviation, the population standard deviation. So let me see. So you want to, it's 0.01 to 15. Okay, so you want to generate two samples like this from normal distribution with a mean of 1 and a population variance of 1. And then sample 2 is drawn from a normal distribution or a population with a normal distribution with a mean of 1 and a population variance of 0.01 squared. So population standard deviation of 0.01. So huge difference in population standard deviation. And then, sample size of 50, sample size of 40, and then do a independent samples t-test, and then repeat the independent samples t-test again, but change the population standard deviation. And basically you want to go in 41 steps from 0.01 to 15. Okay, so in each of these iterations, what you want to do is compute the Levene's test. Levene's test, as I explained earlier in the text in this chapter, is a test for the statistically significant difference in sample standard deviation. So the question is whether this sample has a significantly different standard deviation compared to this sample. Now, for some values of sigma, the answer should be yes, and other values of sigma, the answer should be no. So compute the Levene's test, store the p-value, and then you want to compute two t-statistics. You want to compute the t-statistic assuming equal variance, which we know is going to be not met, right? This assumption of equal variance will be violated for most of these cases, but compute that test anyway, assuming equal variance, and then again, the t-value assuming unequal variance. And then the fourth thing that you want to compute for each iteration in this experiment is the critical t-value using the adjusted degrees of freedom in Welch's method. So here is the formula for the adjusted degrees of freedom. This is the degrees of freedom parameter that you would use when you do not assume equal variance. So when the population, or the two samples, have unequal means and unequal sample sizes and unequal standard deviations, then this is the formula to compute the adjusted degrees of freedom. So there's no Python function to implement this directly, just to compute this. So you have to basically look at this formula. It's a little bit complicated, but it's good practice. So I want you to implement this formula in code to generate the adjusted degrees of freedom in order to compute the critical t-value for a p-value corresponding to 0.05. Okay, so then, this is just talking about the for loop over different values of sigma. And then you want to generate a set of plots that looks like this. So here we see the log of the p-values from Levene's test and as a function of the standard deviation, so sigma for the population. So you can see that the the Levene's test is not statistically significant when the standard deviation of population 2 is somewhere around 1, 2, something like that. But for smaller values and larger values, it is highly significant. So the log of the p-value is very large magnitude negative. So this is when population 2 has a much smaller standard deviation compared to population 1. And this is when population 2 has a much bigger standard deviation compared to 1. Okay, and then this is a really crucial test. Here are the t-values from the two tests, assuming equal variance and unequal variance. And here the dashed horizontal lines correspond to the critical t-values. So you can see that these pairs of t-tests or t-values are kind of comparable, but they're certainly not identical. It's visually obvious that they are close but not identical. And that means that the result of the t-test does depend on whether you assume equal variance or you allow the variance of the two samples to be unequal. Now, I have a few more things to say about this, and I'm going to discuss that in code. So here is where I define the vector of standard deviations. And let's see. So here is the for loop that runs the experiment. So you can see I'm generating two samples from a normal distribution. Here we see the population means, and the population standard deviation is set to 1 for population 1, and then it's going to vary for population 2 according to this vector of standard deviations. And also the sample sizes differ. Okay, so here in the scipy.stats library, we have this Levene test, and we input these two samples. They can be differently sized. They can have different sample sizes. And what we want is the p-value. So I'm going to take the log and store that. Now, by the way, just like a little bracket, you've seen sometimes in these exercises, I ask you to plot the raw p-value, sometimes the log of the p-value, and sometimes minus the log of the p-value. There are sometimes reasons for doing that, like the log stretches out small numbers, so they're easier to see, easier to work with, easier to visualize, and so on. But sometimes, I just add this variability because you see this in the literature, in the scientific literature. Sometimes people log transform their p-values or take the minus log of the p-values. I'm just trying to get you comfortable to multiple different conventions that are used in different disciplines. Okay, anyway, so we store that result, and then here we run the independent two-sample t-test twice. Obviously, the samples are exactly the same. The inputs here are exactly the same. We are just assuming equal variance or unequal variance, and then, getting the t-value from these two cases. And then the final thing is to get the critical t value, which you can see I'm using the inverse survival function. This you've seen before. And then here is the mess of text where I'm implementing the formula that I showed in the slide in the book chapter to compute the adjusted degrees of freedom, and that's what we get here. Okay, and then putting everything together in a plot like this. Okay, so yeah, this is basically showing the same thing that I showed in the book chapter. In that figure, the one thing, a couple things I would like to remark about this. One is that the closer the t-value is to 0, the closer the equal and unequal variance assumption t-tests are to each other. And the further away from 0 we get, so the larger the t-statistic, the more impact assuming equal or unequal variance has. So you can see all of these circles and squares are really closely overlapping, close to 0. And then you get further away from 0, maybe not this case, but many cases further away from 0, and you see that they diverge. Now, the question is not really, it's not a very important question of whether these two tests are numerically identical. They are based on slightly different formulas. So, of course, they're going to be at least trivially a little bit numerically different. The question is whether you would draw a different conclusion about the data based on using equal variance or unequal variance. So we want to look for cases where, one is going to be below the threshold and the other one above the threshold. And that does appear to be the case here once. So it can happen that if you make the wrong assumption about your data, you're going to come to a different conclusion. But you can also see that's not rare. So there it happens once. I'm just running it again here. It's pretty close, but I think these are both on the significant side. I forgot to look at the bottom one. But anyway, you can see, yeah, this doesn't happen super often, but it can happen that you would come to different Here's another case. It can happen that you would come to different conclusions here as well, based on making the appropriate or inappropriate assumptions. And actually, in all of these cases, because the Levine's test is significant for almost all cases, except for a couple around here, it actually is appropriate to use, or it would be more correct to use the unequal variance assumption. So that means that the light gray circles are more accurate, that's more trustworthy than the gray squares. Okay, so there's one final thing that I put in here, which I didn't specify in the instructions, just a little additional way of exploring the impact of this assumption, and that is to compute the ratio of these t-values. So here I'm plotting both of the t-values, and now I'm going to compute the ratio of the two. So can run this code here and generate that plot. And you see if the two t-values were the same, then we would expect a ratio of 1, of course. And if they are different, then you expect a value off of 1. And what you see for these larger standard deviations is that the ratio is consistently above 1, indicating an inflation, an artifactual inflation, a spurious increase in the t-value when assuming equal variance, even though we should not be assuming equal variance. So we are incorrectly assuming equal variance, and the t-value is too high. It's larger than it should be. So I think the grand conclusion from this exercise is that it's probably not a huge deal. In most cases, it won't be a big deal if you assume, if you run the t-test for equal variance, even though the samples have unequal variances, which is to say that you're not going, in most cases, you're not going to draw the wrong conclusion about the data, but, it's super easy to do this the right way. So you should always do it the right way. Here we are with exercise 10 of chapter 11. In this exercise, you are going to compare the parametric t-test and the non-parametric t-test on exactly the same data while running an experiment where you manipulate the distribution shape. It's going to be a super interesting experiment to run. Very insightful. There's going to be one aspect of this exercise that I think you will find a little bit confusing, a little bit counterintuitive. but we're going to work through it together, and I'm going to explain to you why the counterintuitive result is happening, and I hope that that is going to give you a better understanding, a better appreciation for these different measures of statistics on samples. Okay, so here is what you want to do. Let's see. So first, I point out that sometimes these experiments are directly comparable if you're running the same test on the same data and manipulating the sample size, for example. But here we are comparing two completely different algorithms that are entirely different from each other on the same data. So they're not really directly comparable, but I think we can qualitatively compare these two methods, standard parametric t-test and Wilcoxon test, and I think it's going to be pretty interesting. Okay, so here's what you want to do. Simulate 100 data points, so a sample size of 100 as a log normal distribution. So e to the x sigma, where x is just a normal distribution. So 100 numbers randomly drawn from a standard normal distribution, and then times some sigma value that I'll get to in a moment, and then you put that into the natural exponential function that's called a log normal distribution. Okay, and then you want to mean center the sample data. So make sure that this sample has a mean of 0. Okay, and then you want to perform a one sample t-test and a Wilcoxon test against the null hypothesis of 0.5. So that's the main idea. That is one iteration inside this experiment. And then you want to manipulate the values of sigma over different iterations of a for loop, 20 values, starting from 0.1 up to 1.2. Okay, so then you can create a visualization that looks like this. So what are we looking at here? Panel A shows some histograms. This is not all the histograms of all the distributions, just because there's like 20 of them. How many are there? Yeah, there's 20 different data sets. So putting them all in one panel just gets a little bit noisy. So I just skipped some. So this is just every third distribution. The lighter colors correspond to larger values of sigma. Smaller values of sigma correspond to darker colors here. So what you see here is that smaller values of sigma correspond to tighter distributions. You can see this black line here is a very tight distribution, and we get to larger and larger values of sigma, and the distribution gets wider and wider. You have seen this before several times. So this is a typical way that the log normal distribution behaves for different values of sigma. And then, yeah, you can see, well, they're all centered at 0. So a regular log normal distribution is positive only, but here we center the data distributions at 0. And in these vertical dashed lines, I'm plotting the median. So the mean of every distribution is exactly 0 because I forced it to be. But the median, of course, is not exactly 0. I didn't put any constraints on the median. So you can see that the median is shifting to the left. It's getting more and more negative as sigma increases. And I think that's also obvious when you look at the distributions. You have more and more data going to the left of the mean here. Okay, so then, yeah, so then I didn't draw in the H0 value, but it's somewhere around here. So we're testing against, in the t-test, we test against the mean versus 0.5. And for the Wilcoxon test, we are testing against the null hypothesis that the median is 0.5. Okay, so here in panel B, I'm plotting the distance to the H0 value, or the distance to 0.5. Now, for the mean, the distance between the mean of each sample and the null hypothesis value is constant. It's trivially 0.5. That is literally how I defined this sample, to have a mean of 0, and we're testing against H0. So it's trivial that it's a flat line for all these values of sigma. But then, yeah, as I mentioned here, the median is not trivial. We are not placing any constraints on the median. That's based on the shape of the distribution. So as the distribution gets wider and it pulls up to the left, the median is also getting pulled to the left. Therefore, you see that the distance between the median of the distribution and our null hypothesis value is increasing. So it's getting more negative. The median is getting further and further to the left over here. So that's what you see here. Okay, and then here in panel C, I'm plotting the test statistic value from the t-test that you see here with the black squares versus the Wilcoxon z-value. So this is actually not the same quantity on the y-axis, but they're in comparable numerical range, so we can plot them on the same panel. Okay, so then basically you see that as the sigma parameter increases, then the t-test is actually getting smaller. Both the t-value and the z-value are getting smaller. So the smaller sigma is, the more statistically significant these tests are. Now, this is the part of the exercise that is a little bit confusing because you see the median is getting further away. So you might have expected that the further away the median is from the null hypothesis value, the more significant it is, right? That should make sense. So the further away you are from the null hypothesis value, the more significant the result is. That is the intuitive idea, but we see literally exactly the opposite. The further away we get, indicating larger values of sigma, the less significant, still statistically significant, but the smaller the test statistic value. So your next goal here, there's one more plot to create, but basically the goal of this exercise is to understand why we get that counterintuitive result, and also, why the t-test is even changing here, because the numerator of the t-test is literally constant by definition. It cannot change over the course of these different sigmas. Okay, so one more thing to plot here, and that is basically just a different way of plotting panel C. So you plot the distance to the null hypothesis value by the test statistic value, so the t-value or the z-value. I'm also going to have a few things to say about these plots. I will discuss that in the code. So here we are in the code. I create all of the different sigmas, the null hypothesis value, and as I almost always do, this is soft-coded because I want you to have the freedom to continue exploring this code. What happens if you set the null hypothesis value to 0, which is what we set the mean of these distributions to? What happens if you set the mean, the null hypothesis value to 0.5? Okay, let's see. Here is the for loop where I run the experiment. So you can see I'm generating 100 numbers drawn from a standard normal distribution, multiplying it by each value of sigma, and then passing that through the natural exponential function. Here I am subtracting the mean, so I'm forcing the mean to be 0. Okay, and then here I'm computing the sense. This is the center of the distribution, these measure of central tendency. So here we have the mean, sorry, it's actually not the central tendency per se, it is the distance of the central tendency to the null hypothesis value. So the distance from the mean to the null hypothesis value, the distance from the median to the null hypothesis value. Here I am computing the data distribution and drawing the histogram and also a vertical line corresponding to the median. And yeah, you can see I'm skipping every third element, or I'm only running this on every third element. That's really just for visualization. In my opinion, if you have 20 lines on that plot, it just doesn't look very good. It's hard to see anything. So this is also hard-coded, but this is a parameter you could try to play around with. How does it look when you do 6 or 2? Or maybe you don't like this at all. You want to draw every line for you to play around with. Okay, so then we take exactly the same data, exactly the same null hypothesis value, compute the parametric one sample t-test and the Wilcoxon rank test. Okay, and then as I described in the text in this chapter, this is the way to test against the null hypothesis of this H0 value. And essentially what the Wilcoxon test is testing for is whether there is the same number of values to the left of the null hypothesis value versus to the right of the null hypothesis value. So basically the symmetry around the null hypothesis value. And so the way that gets implemented is you subtract the null hypothesis value so that you're just looking at signed symmetry. So how many negative numbers are there and how many positive numbers are there? All right. And then, it's slightly more involved than that, but that's essentially the idea. Okay, and then I generate the plots, the rest of the plots, the rest of the petals. So let's have a look here. So yeah, I mean, this basically just reproduces what I showed. So then, yeah, just to reiterate, what is confusing here is that the null hypothesis value is somewhere around here, right? It's 0.5. And what you see is that as sigma increases, the median gets further to the left, which means that as sigma is increasing here on the x-axis in panel B, the distance from the median to the null hypothesis value is increasing. It's getting further away. And yet the statistical test is getting closer to zero. So that feels counterintuitive. It's also interesting to see that this also happens for the t-test, because this, these black dark gray squares here, this is the numerator of the t-test, literally the numerator of the t-test, the mean of the sample, which is trivially zero, minus the null hypothesis value, which we set to 0.5. So the numerator of the t-test is not changing, and yet the t-value is changing. And it's not due to the sample size, because the sample size is constant. So this can only be due to the sample standard deviation. And why is this happening this way and not the other way? So to gain more insight into this, and also to make another visualization, we're going to basically combine these two panels and plot these statistic values as a function of this distance. And that's the idea of this next plot here. So you can see that here. So the distance to the from the central tendency value to the null hypothesis value by the t-value or z-value. So this is actually the z-value for the Wilcoxon test. Okay, so the x-axis doesn't change, again, trivially, for the t-test, but it does for the Wilcoxon test for the median. Again, the closer we are to the null hypothesis value, the stronger the statistical significance of the result, the larger the z-value. Okay, so I hope that you have figured it out, or at least made a guess, or tried to figure it out, put some effort into it. It is confusing. It also took me a good couple of minutes to figure out why we get this counterintuitive result. Here's the answer. When you look at the distributions, you can see that for small values of sigma, the distributions are really, really tight around zero. They're really narrow, right? The distribution is really narrow. And that means, for this distribution here, for the smallest value of sigma, probably every single point is less than the null hypothesis value. The null hypothesis value is 0.5. Looks to me like every single data point is smaller than the null hypothesis value. And then as sigma increases, the distribution gets wider. The median is shifting to the left because the skew is increasing, but we get, the total dispersion of the data is also wider, which means there's more values to the right or larger than the null hypothesis value. So in statistical tests and inferential statistical tests, the test size, the size of the test statistic, is indeed related to the distance to the null hypothesis value, but that's not all that it's related to. It's also scaled by the variability in the data, the standard deviation, or the mean absolute difference, or whatever is the relevant measure of the distribution or the dispersion of the data. So both of those features combine to give you the statistical result. And sometimes they can compete with each other and give counterintuitive results. So I hope you enjoyed working through this exercise. I know it was a little bit more confusing, a little bit more involved than most of the exercises, but I hope you feel that the conclusion was worth the effort. Here we are in exercise 11 of chapter 11. The goal of this exercise is to explore the relationship between the p-value and the effect size. Now, this is a little bit confusing for people who are new to statistics when you're first learning about statistics, because people often think that the p-value is basically a measure of effect size. So the smaller the p-value, the bigger the effect. That is not necessarily the case. It can be the case. It can be that larger effect sizes have smaller p-values, but there's no trivial relationship between the two measures for reasons that I hope will become clear by the end of this exercise. Okay, so let's see. A lot of the code for this exercise you can copy from exercise 6. of this chapter. So you might want to make sure you've done that exercise before doing this one, and then see what you want to copy and paste here. Okay, so what you want to do is, compute one sample t-tests on data from a range of population means. So this is going to be our measure of effect size, the true underlying population mean, and we're going to vary the sample size. So here, let's see, you can have the population means vary between 0 and 2 in 71 steps. In exercise 6, we ran 250 samples over and over again just to get some variety. But here we're already getting a lot of variety by sampling from populations with different means and also different sample sizes. So you can just do one run, one iteration per mean, population mean per sample size. Okay, and then let's see. So what you want to do is, so you don't need to store the binary significance outcome. Instead, you want the actual p-value. And then you also want to compute Cohen's d. This is a measure of effect size for a t-test, not this Cohen, it's some other Cohen. There's too many Cohens around. Cohen's d and r squared. According to these equations, I will scroll up in a moment and show you these equations. First, I want to show you the plot. So basically, you're going to need a double for loop to manipulate the population mean and also the sample size. And then inside that for loop, you compute these three. You perform a t-test on some data that you generate, and then compute and store the p-value, Cohen's d, and r squared. Okay, hope that makes sense. And then basically you want to plot them. So what you see here in panel A is the p-value, and I took the log of the p-value just because these p-values get really small, so they're really stretched out. So the log of the p-value is on the x-axis, and our measure of effect size, Cohen's d, is on the y-axis. And I'll have a few more interpretational comments about this that I'll discuss in the code. Here you see the plot of Cohen's d by r squared. So these are two different measures of effect size. And I didn't do this here, but if you want, you could also plot the r squared by the log of p, the p-value here. So basically reproducing this panel, but for r squared instead of Cohen's d, if you like. All right, so I'm going to scroll up and show you these two formulas to compute these measures of effect size. Here are three different formulas to compute Cohen's d, depending on whether you're doing a one sample, a paired samples, or a two independent samples t-test. Now, in this case, we're only doing a one sample t-test, so lucky for you, you don't need to implement this really big formula here. So it's just this, very simple. It's the sample mean minus the null hypothesis value divided by the sample standard deviation. Okay, so that is Cohen's d. And then we can scroll down to get r squared. So our measure of r squared for the t-test is the t-value squared divided by the t-value squared plus the degrees of freedom. Okay, so those are the two measures of effect size that you implement here and compare against the p-value for a range of population means and a range of sample sizes. So here are the population means that we will use. And this is the range of sample sizes. This is taken from exercise 6. Okay, here you can see I'm initializing the three measures that we will store for each iteration in this experiment: the p-value, Cohen's d, and r squared. Here I have a double for loop. I'm manipulating the sample size and the population mean, drawing the distribution. Again, some of these parameters I didn't specify right now, but they are in the instructions for exercise 6. Okay, so here we perform the t-test against 0. Here I store the p-value. Here I compute the Cohen's d. So very simple. It's just the mean of the sample. Now, we would say minus the null hypothesis value, but the null hypothesis value is 0. And divided by the sample standard deviation. And here's the r squared, also very easy to implement. All right, so run this experiment. And then here I'm generating the plot here. All right, so a couple things to remark. First of all, there is no trivial relationship between the p-value and the effect size. That is to say, for any given p-value, you can have a very large range of effect sizes, right? So for the same p-value, the log of minus 20, whatever number that is, but it's a very, very small p-value. You can have a really tiny effect size. This is like 0.3 or something. Or you can have a really large effect size. Well, not super large, but this is quite a respectable effect size here of 1. So very large range. Another interesting thing to remark here is that it's not a disorganized cloud, this relationship. In fact, it looks like there are multiple streams where there are relationships between the p-value and the effect size. And so it turns out that each one of these corresponds to a different sample size. So if you have the same sample size, if you hold the sample size fixed, then there is a tight relationship between the p-value and the Cohen's d. But that's not the way that it works in practice. You don't collect many different samples of exactly the same sample size that vary systematically in their population mean. Instead, you just get one sample. So the point is, there are some complicated relationships between p-value and effect size, but it depends on a variety of factors. You could also, by the way, manipulate the sample standard deviation here if you want. You could manipulate this. So instead of manipulating the sample size, so this would be, just an interesting follow-up for you to do. Keep the sample size fixed and vary the or the population standard deviation. It's another interesting thing you could explore here. Okay, so given a p-value, you cannot know what is the effect size. That is the main point here. If you have a certain p-value, you don't know what the effect size is. You have to compute the effect size separately. You also see there's something funny going on here, and basically that's for the smallest p-values that are so close to 0, basically because the sample size is getting large and the mean effect is getting large. So these samples are so close to 0 that they effectively are 0, and that's why I had to add this tiny, tiny number to the p-value so that I don't get a warning message when I take the log of what is essentially 0. I hope that's clear. That's the main take-home message here. This, I wanted to show you that there is a relationship between these two different measures of effect size, Cohen's d and r squared. It's a nonlinear relationship, and that is because Cohen's d is not bound by any particular number. We typically just take the absolute value so that it's bound by 0, but the formula itself is not bound by 0. But anyway, so Cohen's d can be larger than 1. R squared cannot be larger than 1. So there is a pretty tight relationship. You can see it's not perfect. It also depends on a variety of features like the sample size and so on, and the sample standard deviation. But so these two different measures of effect size are related to each other, but you need to interpret each one separately because, an r squared of 0.8 is Cohen's d of almost 2. Exercise 12 and 13 is basically just one project, but I split it up into 2 separate exercises. The goal of this exercise, exercise 12, is to import and process a data set from online, real data, not simulated data. But we're not going to do any statistical analyses here. In the next exercise, we will do some statistical analyses. We'll run a bunch of t-tests, compare for multiple comparisons, and so on. So about this exercise, so I want you to do this exercise in Pandas and Seaborn to gain more familiarity with importing and working with data in Pandas. If you're not super familiar with the Pandas library and working with Pandas data frames, then it's fine. It's really not about statistics. It's just about some like housekeeping stuff in Python. So if you're struggling with the coding and data organization aspects of this exercise, don't worry about it. Just check out my code online. It's not a big deal. This is more about coding than about statistics per se. All right, so let me tell you about the data and what you should do in this exercise. This is a data set that you get for free online from the University of California, Irvine Machine Learning Data Repository. And it's all about predictors of wine quality. So it's 1,600 observations with a bunch of features about the wine. So acidity, sugar, alcohol, and so on. And then there is one variable on subjective quality ratings, and that is going to be our key dependent variable. And the question is whether any of these uh, wine chemistry features are related to the subjective rating of the wine quality. Okay, so let's see. So in the footnote, I have the URL. The URL is, of course, also in the online code. So you can read more about the data if you like, but you don't need to know anything more than what I just told you. Okay, so a couple things you need to do. Import the CSV file from the web. Again, the URL, the direct URL to the CSV file is in the online code. I also print it down here at the bottom of the book, this page. And yeah, import the pandas data frame and have a look at it. So here you see the characteristics for the different features of this data set. Basically, you should get a screen that looks like this. And then you know that you have successfully imported and described the data set. And then the next thing you want to do is compute and print the number of unique data values for each data feature. So you can print out a table that looks something like this. So fixed acidity. So this is one of the variables in the data set called fixed acidity, and it has 96 unique values. This is not a distribution. This is not a histogram. This is not the mean or anything like this. This is just the number of unique values in the data. So some have more unique values, some have fewer unique values. We can look down here at quality. This has only 6 unique values. And actually, because this is the t-test chapter, we are going to be performing a t-test using this as the dependent variable. The independent variable. So this is going to be our independent variable. But as you know, with a t-test, we can only use a t-test if there is one sample or if there are 2 samples. And so there is no t-test for 6 samples. So what we're going to do is basically perform a median split on these data according to low quality versus high quality. And I'll talk about that in a moment. Okay, let's see. Yeah, you can use some visualizations. You can use Seaborn's box plot method to visualize all the data. And basically, you will see that the data have very different numerical scales. All these columns in the data set are in their own unique scale. So sugar and pH are not in the same numerical scale. Okay, so figure out a way to z-score all of the columns, although you don't want to z-score the quality column for reasons that I will explain in a moment. Okay, then the question is, do these data conform to the distributional assumptions of a t-test? So you can use either the Shapiro-Wilk test or the omnibus test to test against the null hypothesis that the data are normally distributed. In every single case, the data are highly significantly non-normally distributed. So they're significantly different from a normal distribution. But what does that mean? You know, these are just numbers and they're actually all zeros. But remember, we have a huge sample size, 1,600 data points. And I've mentioned in the text earlier in this chapter that these measures, these statistical measures of distribution shape are not really that great. They work well for relatively small sample sizes on the order of tens, a couple of tens for a sample size. But once the sample size starts getting big, basically what happens is these tests are so sensitive that tiny, like minuscule differences from a standard normal distribution are going to give you a significant result. So let's have a look at the distributions here. Okay, so what you see are histograms for all of the variables, including quality. And basically what you see is, yeah, okay, I mean, some of them, this one looks really quite normal. This one looks quite normal. But, this distribution here looks very normal to me. This has a p-value of less than 0.0000. So according to the Shapiro-Wilk test, this is extremely statistically significantly different from a normal distribution. Again, that's really just due to the very large sample size and the sensitivity of these tests to really large samples. So this is another illustration of why it's so important to visually inspect your data and not just trust a bunch of numbers that you get out of some Python function. Okay, anyway, other of these variables are less normally distributed, but almost all of these distributions have normal-like properties, right? There's one peak, and mostly, sort of goes down on both sides. So what should we do about this? You could apply a transformation. You could apply the log transform, but I don't think you want to log transform pH or density. And maybe you could log transform the total sulfur dioxide, but would you log transform volatile acidity? I don't know. So what I think we should do is not apply any transformation, and instead try both a parametric t-test and a non-parametric t-test, and see if we get different results from those two measures, which make different assumptions about the distribution. So that's what we're going to do in the next exercise. Okay, then I would like to direct your attention here to the quality. You see there's only a couple of values, but it's perfectly distributed around the median. So basically what you're going to do is perform a median split on these data, on the quality data, to create another column in the data frame that is 0 for low quality, so these values here, or 1 for high quality, which is these values over here. So you can call it 0 or 1, you can call it false and true, you can call it A and B, or low and high, whatever you want. And then this is going to be the main independent variable that we will use in the next exercise. Okay, so then, so that is it for this exercise. I hope you enjoy working through it. As I mentioned, it's just a lot of housekeeping stuff in Pandas. If you're stuck with the code, feel free to check out my online solution, which I will now go over with you. So here is the citation, and here is the direct link right to the website that has all the information about this data set. So importing a CSV file from online is super simple in Pandas. Use the function read CSV. You input the URL, and you have to specify the separator of each column. So you do need to download this file yourself and look through the text file and understand what's going on in there. But once you do that, it is pretty easy to work with. Okay, so this is just, some rows of the data. And here I'm using the describe method on this data frame that I call variable data. And this is a pretty handy method. It gives you a list of the main descriptive statistics for all the different columns. And, if you want, you can look into this method more. There's some optional input parameters you can provide to give more or fewer descriptions, to specify only some of the variables, and so on. Okay, so then here I'm listing the number of unique values here, and basically I'm just saying, for each column, so the labels of the column and how many unique values, so the number of unique values that are in each of those columns. This is also just a useful way to investigate a data set. Okay, so now I'm going to generate a box plot using Seaborn, and that you see here. Now, what you see is mostly a lot of just flat lines, right? The thing is that these data are in such different numerical scales that it's hard to see the variability in any of these variables. It's really all driven by total sulfur dioxide. You can also see there's a couple of outliers in here. I have a line here to remove these two outliers based on visual inspection. I didn't include that in the exercise, but you're welcome to try and see whether the results are different if you uncomment this line and remove these two data points right here. Okay, so for now, I'm going to z-score all of the variables except for this one. So you can see I'm looping through all of the columns except for this one here, except for quality. And then I compute the mean of the column, the standard deviation of the column, and here I implement the z-score method manually because it's such a simple thing to do. It's such a simple computation. What you can also see here is that I'm overwriting the variable. So that means after I run this cell, I will no longer have the original data in their original units. In this case, that's fine. I don't need the original units, but it's something to be aware of. If you want to Z-score, but you also need the original units, then you might want to create a new data set. Maybe you could call this data Z for these Zs transformed. Okay, so then, we can redescribe the data. You can see that the means are all zeros, the standard deviations are all ones. And so this is just to show you can also implement this without the for loop here. Okay, and then when we recreate the box plot, now we see that we get a much better picture of what's going on for all of these different variables. Now, it may appear that there's a ton of outliers, right? This is Z values. So you can see some of these values go up above 10, but I don't know if these are really outliers per se. The thing is that the distributions for some of these variables are skewed to the right. So I would be a little bit reluctant to remove, all the values above 3, for example, because I think that these are real parts of the data that we don't want to reject. It's just that these data have a positive skew to them. Okay, so now here's the code where we test for normality. This code is pretty straightforward, actually. As I mentioned, they're all highly significant. But when we look at the histograms, you can see I'm using that, or implementing that using Seaborn to generate the histograms, and then switching off the axis ticks. Yeah, I mean, they don't look like perfect Gaussians, but most of these variables look fairly reasonably normally distributed to me. All right, so here is the code where I do a median split on the quality metric over here. And you can see, let me show you this bar plot before I explain the code. So here's a bar plot. This is actually exactly the same as this plot here. It's just expanded and with the numbers in here. So basically, I chose a value of 5 or 5.5 as the split. So I create a new column where I set all the values in that column to be false. It's called bool quality for Boolean. And then basically any of those data values, any of those rows where the quality, the numerical quality is greater than 5, so it's going to be all of these, I set that to be true. So it's going to be true for large, highly rated wines and false for low rated wines. And yeah, so here you see the data set just with those two columns. So that's it for this exercise. I hope you found this useful for gaining more familiarity with pandas. And now in the next exercise, we're going to run a bunch of t-tests on these data. Here we are in exercise 13 of chapter 11. This exercise follows directly from the previous exercise where we imported and processed this data set about wine quality and predictors of wine quality. And now in this exercise, we are going to perform statistical tests on that data set. In particular, we want to know which of these wine features, wine chemistry features, are significantly different between wines that were rated as low quality versus wines that were rated as high quality. So we have two groups. We have the low quality wines and the high quality wines, and they're not paired. It's not the same wine that is rated once low quality and then the next time high quality. It's different wines. So therefore, we need to run independent two-sample t-tests. Okay, so you want to do two-sample t-tests using a parametric t-test, and then reproduce the results using a non-parametric t-test to see whether it matters because of the discussions about the slightly non-normal distributions that we discovered in the previous exercise. Now, because we are performing multiple tests on the same data, in the same data set, you need to correct for multiple comparisons. So you can correct for multiple comparisons twice using Bonferroni correction and using FDR correction. And then the result of this exercise is going to be to print out some text that looks like this, a table. So we have the variables here, the t values with the degrees of freedom and the t score, the t value. And remember, this is the difference between low quality and high quality wines. And then we have the p-value. Now, this is the uncorrected p-value in all of these cases. It's uncorrected for multiple comparisons. So then after that, you can add two markers here. So we have an asterisk if it is significant for Bonferroni correction, and a plus sign if it's significant for using FDR correction. So in almost all cases, the significance result came out the same. But we do have this one interesting case where this result would be considered statistically significant when using FDR correction, but not when using Bonferroni correction. And the difference between FDR and Bonferroni is something we've discussed before. It was the topic of one of the exercises previously. Okay, so this is your goal. Now, getting most of this to print out is not so difficult. It's just a bit of coding, copy paste from code you've seen earlier in this chapter. It gets a little bit tricky to do the FDR correction, the Bonferroni correction. The key insight here is that for the FDR correction, you need to have all of the p-values. So if you're running all of these in a for loop, you're going to need to store all of the p-values. And then after that for loop where you compute each of the p-values, then you can do your FDR correction. Okay, so generate this table using a parametric t-test, and then reproduce this using the Mann-Whitney u-test. That is the non-parametric analog of the two independent samples t-test. And then what you want to see is whether the conclusion you would draw about the data would change. So not the p-value per se, because of course the p-values will differ. These are different algorithms that we're applying to the data, so the numbers will differ. The question is whether the conclusions you would draw from the data would be different depending on whether you use a t-test or the Mann-Whitney u-test. There's a lot of other things you can try. You can try without Z transforming the data, and all sorts of things you can continue working on. But now I'm going to show you my code solution and basically just show you how I implemented this. All right, so here is the code. And let's see. So I'm initializing a dictionary. There's many ways to implement this exercise correctly. I'm going to show you the way that I chose to implement it. If you implement it in a different way, then that's great. I like to show variety in my solutions so you don't get stuck into this idea that statistics can only be coded in one way. There's many correct ways to code problems and solve problems in statistics. Okay, so let's see. Here I'm looping over the columns in the data. This is just the columns that I Z-scored, which excludes the quality column, which is good because that's the main independent variable. So we don't want to use that in the data as well. So now this is really the key line here. So we want the independent samples t-test. And here I'm just extracting the data from this column for the high rated wines and the low rated wines. And these are variables just for convenience. So X data for high and for low. And that's just so I don't need to write out all of this text all these times here. So this is the key line of code here. Now, and then I'm extracting the t-value and the p-value. Now, the thing is that this function does not output the degrees of freedom. I cannot tell you why that is the case. That is a choice that the developers made. But I want the degrees of freedom because I want to report the degrees of freedom. So I had to compute the degrees of freedom using Welch's method based on assuming unequal variance. There was another exercise earlier in this chapter where you implemented this formula to compute the corrected degrees of freedom. Okay, so this gets all of the value. Oh yeah, and this is for the Mann-Whitney u-test. So I'll come back to this later. Okay, so I ran this code, and now I have all of the p-values, and now I can use FDR correction. Okay, so then here is Bonferroni and FDR correction, as you have seen, implemented in a previous exercise. But then once we get this, then we know whether these results are significant using each of these correction methods. And so here's like a kind of cleverish way that I've implemented this. Basically, it's going to choose whether to print a space or the symbol, depending on whether this is false or true. So if the p-value is less than the Bonferroni threshold, then this result ends up being true. It gets converted into a 1, and then that is the index here to take this asterisk. Okay, and then this is what I showed in the book. So then the next thing I want to do is basically just uncomment this line and rerun everything. But first I want to save all of these. So I think I will copy and paste this like this. And now when I run this cell here, this is going to be overwritten. These are the new values. So now we can compare the parametric t-test results with the non-parametric Mann-Whitney U test results. Now forget about this. This is actually incorrect. These are not t-values. So ignore these values. What we care about are not even really the p-values, because, yeah, as I mentioned, the numerical statistical values will change. These are completely distinct algorithms for performing statistics. What we want to know is, are there cases where using a t-test would give us one conclusion about the data versus we use the Mann-Whitney U test and we come to a different conclusion about the data? And the answer is no. In none of these cases, even this edge case here, where it was significant with FDR and non-significant with Bonferroni, even that is exactly the same. So the pattern of results, the way that we would interpret the data is the same, even though the statistical algorithm is different. In my mind, that's very heartwarming. I really like to see these kinds of results because it suggests that we are looking at a real effect in the data and not just some weird quirk of applying a particular algorithm.